Okay, hello and welcome everyone. So in this video, I'm going to do a walkthrough of the three portions for the first exam in intermediate micro. So the first part was the multiple choice, and then there's the two short answer components. So I'm just going to go through all the multiple choice questions. One of the things I realize is that your multiple choice might have shown up in a different order. So what I always do is I just hit like Command F to find on my page and then search for whatever word you're looking for, and that'll zoom down to or you could just scroll through or whatever. I don't know. Maybe that's just me being old. I don't know. Okay, so given a price increase in good X, there's a substitution effect. There's an income effect on the demand for good X. So that's just what happens when there's a price increase. There's going to be a change in demand or a change in quantity demanded, and that change in quantity demanded is due to what we'll call the substitution effect and what we call the income effect. Then what we want to do is we want to identify from amongst the choices which of these is consistent with that. It actually turns out it's this one. So though the substitution effect is always negative, the income effect can be either positive or negative. In fact, this is true just by definition. And so I had the slide where I was showing kind of like the separating out the effect of the price change into the substitution effect and the income effect. We always had with a price increase, substitution effect would lead towards a decrease in the quantity demanded of that particular good. The income effect could lead to an increase or decrease. It could be positive or negative according to whether we've got a normal or an inferior good. And so this is just true by definition of substitution effect and income effect. I kind of made for that one. I meant for that one to be hopefully relatively straightforward. All right, so Max is able to spend his screen time watching the movie Frozen. F is the quantity of Frozen, or the movie Polar Express. E. If Max optimizes subject to his budget of available screen time by choosing consumption where the ratio of the price is PF, price of Frozen, divided by PE, price of Polar Express, in terms of screen time points, is less than the ratio of marginal utilities of Frozen and marginal utility of Polar Express. That's this right here. Then what's true about Max's consumption? Well, so the first thing we want to do is we want to just take the quantities that have been given, that this is the price ratio. So I've written this down. And then the marginal utilities, that's this right here. So we have price ratio, we have MRS, and we are comparing them, but we're told how we're comparing them. Max is currently optimizing in a situation where the ratio of prices is less than the MRS. So I've got this here. Okay, now before I think about identifying which is correct from here, we need some additional information. We're told these goods it's either or. In some sense, this is sort of invoking substitutes, but what's really driving home our understanding that we're dealing with substitutes is we are told Max is optimizing. Max is optimizing by choosing consumption where we have specifically a situation where price ratio is going to be less than the MRS. Well, if this was an interior solution, the price ratio would have to be equal to the MRS, right? We'd have a tangency condition for optimizing. No, that's not what's happening here. Instead, we have this degenerate situation. We have a corner situation where Max is optimizing with a bundle that is making the marginal rate of substitution bigger than the price ratio. That can only happen and be optimal with perfect subs. And indeed, when that happens, we would get what we call our Alex solution in this under these circumstances. This would be watching only Frozen and not Polar Express. We actually don't need the all X. We actually don't need the graph. The reason why I drew the graph like this is we're thinking of like PX over PY. So this is like F is our X and E is our Y. So that's why I drew it this way. We actually don't need the graph at all. And we wouldn't really, what we need to be able to solve this is we need the comparison of price ratio to MRS. We also need to know that Max is currently optimizing, and then we just need to interpret what's happening here. So if we're at a situation where Max is optimizing and the marginal rate of substitution between Frozen and Polar Express is bigger than the price ratio, this must be a situation where Max is consuming only X. If it was a situation, so we can easily rule out it being, that they're having equal amounts. So how do we know that's not going the other direction? How do we know that it's not a situation where Max is consuming a bundle that's only Polar Express? Well, if that was the case, that wouldn't be optimal given what we've been told about how these are related. And actually, I don't even know if that was amongst the choices. No. We know they're not watching sum of both because it's not optimal if we have a situation where the price ratio and the MRS is not equal. In order to have somewhere on the budget constraint being optimal, that's not corner solution, you need for the indifference curve to lie coincident with the budget constraint. All right. Question 3, Jack is consuming gum and candy. Originally, we could depict Jack's budget line as C is equal to 20 minus 2G. Subsequently, we could depict Jack's budget line as C is equal to 10 minus G. We can describe the change between the two budget lines as due to, well, that's this picture right here. This is initially Jack's budget constraint. This is the subsequent Jack's budget constraint. And what's happened is, well, the vertical intercept has gone down from 20 to 10. Horizontal intercept stayed the same. The gum intercept has stayed the same. The candy intercept has changed. And so we're thinking about what's happened here. Well, it's a combination of effects. So this downward arrow, this portion is driven by our income decrease, right? So a decrease in income. We know income's decreasing because the income is represented by this 10 and by this 20, right? 2 is the PG and 1 is the PC, right? The price on candy is 1, the price on gum is 2. If we were to arrange this to look in standard budget constraint notation, we'd see clearly that M is 20. Here M is 10. Okay, so income has fallen. We've got that. And then this is weird because this intercept changes, but this one doesn't. Well, what's happened is this is coupled with a situation where the price of gum has fallen. So this is going to balance off and then lead to a situation where the maximal amount of gum that Jack can consume hasn't changed. So here's an example consistent with this. We have income 1 is 20, income 2 is 10, price of good 1 is 2, price of good 2 is 1. So the maximal amount that we could consume of good 1 would be M over P1. So 20 over 2 initially, it's 10. And then 10 over 1 subsequently, still 10. So that is why the answer is Jack's income has decreased and the price of gum has decreased. Okay, question 4. So Owen is insisting on consuming 2 units of good Y per unit of good X. If the price of good X is 5 and the price of good Y is 6, then with M dollars of income, Owen's demand for good X will be. All right, so the first thing we have to do is we are told Owen insists on consuming 2 units of Y with each unit of good X. This is telling us we've got perfect complements, we've got fixed proportions for consumption, utility coming from good X and good Y. The next thing is you got to determine, is this going to be a utility function is going to be the minimum of 2x and y, or is it going to be the minimum of x and 2y? Well, I have a walkthrough video where I show kind of like how to test some bundles and then look and see. The quicker version is just to say, okay, well, I know it's actually this. Let me verify by choosing one bundle that I know that Owen would like. We were literally told 1x with 2y. So Owen likes this bundle. X is 1, y is 2. Let's drop this into my utility function, make sure it works, right? So Owen's utility is going to, over this bundle, 1, 2, is going to be whichever is the smaller of 2 times 1 and 2. That's 2 on both sides, so there is no waste, there is no inefficiency. So we know indeed this is the correct preference representation. All right. So the next thing we want to do is actually find Owen's demand. I need to build my budget constraint. So the budget constraint, here's my utility function. Here's subject to my budget constraint. This is the maximization problem. I should have said max by choosing x and y. I didn't. Anyway, so the next thing I'm going to do is I'm going to say, well, here I have the perfect complements utility. I can replace this comma with an equal sign, and then that'll give me the line through the corners of my indifference curves that the solution's got to be on. That gives me a system of equations, two equations, 2 unknowns. I can solve by substitution. So I'm gonna put this equation, which links the corners of my right angle indifference curves, into my budget constraint, and then I can solve. So I'm gonna have 5x plus 12x is m, or 17x is m. M over 17 is my demand for good x, and so that is this right here. Owen's demand for good x is m over 17. Good. It didn't ask for it, but Owen's demand for good y is going to be 2m over 17, and then we'll plug this into the utility function, and Owen's utility from that bundle from m over 17 and 2m over 17 will be 2m over 17. All right. Question 5, Emily has 44 units of income. Emily's utility over these three goods is given by the smaller of x1, 5x2, 2x3. I'm laughing at all my numbers I've got there. If the price of good 1 is $1, price of good 2 is $15, price of good 3 is $7, how much of good 1 does Emily obtain? This is a situation where we want to take our economic intuition for approaching these problems as portable. So we have perfect complements, but embedded into perfect complements is this perfect substitutes feature, right? So good 2 and good 3 have some substitutability. Good 1 and then good 2 and 3 are complements. All right. And so what's going to be the easiest way to approach this problem? Well, the first thing I do is let's just get our information on the table. So we have 44 units of income. Price of good 1 is 1. Price of good 2 is 15. Price of good 3 is 7. Good. That gives me my budget constraint. X1 plus 15x2 plus 7x3 is equal to our income of 44. And we are going to require, like, let's try my trick. Let's replace this comma with an equal sign. I'm going to require this relationship. But then I'm saying, wait a second. There's something weird going on over here. I've got the substitutability. And I want to think about what I know about how substitutes behave. And so this is part 1, part 2, part 3, part 4. I'm going to say, all right, let's look at these substitutes. Let's take this really seriously. And let's think about the substitutability between good 2 and good 3. In matter of fact, let me write down the MRS between good 2 and good 3. So the MRS between 2 and 3, the marginal utility of good 2, marginal utility of good 3 is going to be 5 over 2. And then let me compare this to the price ratio. 2 over 3, well, that's going to be 15 over 7. And we see, 5 divided by 2 is 2.5. 15 divided by 7, I don't know what that is, but it's smaller than 2.5. So this would be an all x2 solution, right? This would be the situation where, given the ability to drive my utility from either good 2 or good 3, Emily's going to drive Emily's utility from good 2, right? Here's the picture that corresponds. All right, so we know that Emily's going to be biased towards good 2, away from good 3. And so now what I'm going to do is I'm going to change this relationship. And rather than having x1 is equal to 5x2 plus 2x3, I'm going to write this as x1 is equal to 5x2 plus 2 times 0. And so this is going to be x1 is equal to 5x2. And then solving, we find, solving by substitution into the budget constraint, we can find Emily's demand for good 2 is going to be 44 over 20. All right, I don't want to deal with that fraction, but it turns out I don't need to, because I can take 44 over 20 and I can bring this back into my relationship. X1 is equal to 5x2, so I'm going to multiply numerator to numerator by 5. Okay, 44 times 5 is 220, and I'm going to have 220 divided by 20, which I can do in my head, is the demand for good 1. All right. So a couple things here. First off, I think it's kind of a cool question. Also, look how you can work with the fractions, and you can do this all, more or less without calculators. So, anyway, good work to this point. Question 6, or 6 on this set. Joey's utility is quasi-linear. It's going to be 2 times the natural log of x plus y. Given Joey's income and the relative prices, Joey is buying 10 units of good x, 15 units of good y. Suppose Joey's income doubles while the prices remain the same. How many units of good x will Joey buy after the income changes? This is actually like a quasi-linear demand question, but here's how we can solve this. Let's get the marginal rate of substitution. That's going to be the partial derivative of this utility function with respect to x. So the derivative of the natural log of x, 1 over x, times 2 makes it 2 over x. Divide this by the partial here with respect to y, that's 1, so 2 over x divided by 1 is just 2 over x. Compare this to my price ratio, px over py, and then solving for x star, for my demand for good x. Oh, wait a second. My demand for good x only depends on the relative prices, but the prices remain the same. So what's going to happen after Joey's income changes? Nothing. It's invariant to changes in income. Joey's demand is going to remain at 10. All right. Because Joey's income's doubled, actually what's going to happen is Joey's going to buy Joey's 10 units of good x, and then Joey's going to just start buying good y with the additional income to satisfy the budget constraint. But I didn't ask you that. I just asked what happens to x. All right, so question 7. Ani consumes peanut butter and dog food and nothing else. When the price of peanut butter rises with no change in Ani's income or the price of dog food, Ani buys less dog food and less peanut butter. What can we say about Ani's consumption? Well, the price of peanut butter has risen. This makes Ani relatively poor, and Ani's buying less dog food. Ani's purchasing power is going down, right? Relatively poor by buying peanut butter because the price of peanut butter has risen. Now, relatively speaking, Ani has less money available to buy anything else. And since Ani is becoming poorer and buys less dog food, when income falls and you buy less of a good, that's a normal good. So this is telling us dog food must be a normal good, right? So what's happening to peanut butter? Well, when the price of peanut butter rises, Ani's buying less peanut butter. That's just a law of demand story. Price rises, quantity demanded falls. We can't really say that peanut butter is a normal good to Ani. Could be. It's at least consistent with it being normal. However, it could still be an inferior good with a stronger substitution effect, right? So it could be an inferior good, and peanut butter could be an inferior good to Ani, and Ani still buys less because of the stronger substitution effect. What about this? So peanut butter is an inferior good to Ani. Well, peanut butter's dynamics are actually more consistent with it being a normal good, buying less when poorer. We'd actually need Ani to be buying more when becoming relatively poor peanut butter, and that didn't happen. And so of these, the rest of them just really aren't that great answer. The only one that we can say without additional structure and additional assumptions is that dog food is a normal good to Ani. We're told exactly these dynamics, and so that's this one. Let me see if I have Ani. Oh, there we go. There's our puppy study break. There is Ani. Look, Ani is wondering when are we gonna get on the sidewalk and go for a walk? That's what Ani's wondering. All right. So question 8: Max consumes two goods, has positive income, positive prices. Suppose Max's income doubles and both prices triple. What happens? Well, Max's budget is going to shift inward towards the origin. The slope's not going to change, right? Triple the price of both goods, and both goods are going to be affected the same way. All these dynamics taken together is essentially going to look like this. The intercepts for good 1 and good 2 are going to be of the form m divided by pi. Well, we're doubling income, we're tripling prices, so it's going to be like multiplying each of these intercepts by 0.67. Well, that's going to end up shifting the budget line inward without affecting the slope. Question 9: Laura buys only good X and good Y, has preferences represented by Cobb-Douglas utility. Which do we know about Laura's demand? Well, here's our general Cobb-Douglas demands. They depend only on this collection of constants that are going to correspond to the coefficients. Remember, it's like X to the alpha, Y to the beta is Cobb-Douglas. Laura's demand for good X is going to be m over px, and then Laura's demand for good Y is going to be m over py. Where did this come from? Well, you could set up the Lagrangian, or you could do the standard Cobb-Douglas utility maximization problem and recover the Marshallian demands. Basically, we're just asking about Laura's demand functions. Yeah, the demands for the goods depend only on Laura's income and the price of the good itself. We've gone over this quite a bit in class. Notice Laura's demand for good X is going to be a constant share of Laura's income. Right? Sorry, Laura's expenditure on good X is going to be a constant share of Laura's income. To get expenditure, we just multiply through by px. We'd write this as px x star is equal to alpha over alpha plus beta times m. And Laura's expenditure on good Y is going to be a constant share of Laura's income. It's going to be pyy is Laura's expenditure on Y, and then beta over alpha plus beta m would be that share. All right, Jenny's preferences are represented by whichever is the smaller of x plus 6y and 2x plus y. So this right here is perfect complements with this substitutability embedded in it. It gives these nice sort of winged indifference curves. The steeper ones are going to have an MRS, a slope of 2, technically minus 2. The flatter ones are going to have an MRS or a slope of minus 1/6, right? So I wrote this in absolute value, right? So all right, no big deal. What we want to do is we want to find the slope of Jenny's indifference curve at the point 77 if we have x on the horizontal and we have y on the vertical. So the easiest thing you could do is you could just evaluate the utility function at that point, right? So just take utility of 77, it's going to be 49 on this side and it's going to be 21 on this side. The smaller of the two is driven by this side of the indifference curve of the utility function, and the slope of this thing, the marginal utility, is 2. So that's the answer. Right. The other thing you could do, slightly more complicated, is you could replace this comma with an equal sign. You can get the line through these corners, They still have corners, and we're going to still find the line through them. This is the line y is equal to 1/5 x. Good. Then we could evaluate this point relative to that line. And if you do that, you're going to say, oh, for an x of 7, the plotted or predicted y is going to be 7/5, but the actual ordered pair is 7, so we know it's going to be above that line. And so so I could drew this here. Here's my x is 7. Here's where the line is, it's 7/5, but here's where the point itself is, it's 7/7. We see that this is higher than this line, and points higher than the line have a slope of 2. Points lower than the line have a slope of 1/6. There's kind of two very closely related ways to answer the question. All right, question 11. Jack's utility is represented by 32xy. Jack's currently consuming 10 units of good x, 8 units of good y. Max's utility function is 3x plus 5y. Max has 9 units of x and 13 units of good y. So what I'm going to do is we're comparing their utilities, their preferences for the given bundles. So here is Jack's utility for Jack's bundle. It's going to be 32 times 80. Here's Jack's utility for Max's bundle. It's going to be 32 times like 117. Okay, Jack likes Max's bundle better. All right, here's Max's utility for Jack's bundle. It's going to be 30 plus 40 is 70. Here's Max's utility for Max's bundle. It's going to be 27 plus 65 is 135. 65. I used to run 5 13-mile days when I was running high school track. So I had 65-mile weeks. I'd run 5 days a week. Took off Fridays and Sundays. Anyway, so the answer is Jack prefers Max's bundle to Jack's. Max prefers Max's bundle to Jack's. Max prefers Max's. Jack prefers Max's. Yeah. Okay. All right. Ben regulates the amount of time Jack is able to spend on the computer. Jack has earned a certain number of points that Jack can use to buy screen time for either Minecraft or Roblox. Jack's marginal rate of substitution between these activities is 1. On Saturday, Jack optimized by spending 15 minutes of Roblox, 45 minutes on Minecraft. You know, as a result, well, this is an interior solution. The MRS is 1. Jack's got a positive amount of both goods. It's got to be an interior solution. For that to be optimal, it must be the case that the MRS of 1 is equal to the price ratio, which also has to be 1. So that tells us the prices of both goods is the same, and hence the answer is Roblox and Minecraft cost Jack the same number of points, which is true. Eden has the utility function 2x plus y. If the price of good x is $1 and price of good y is 50 cents, what do we know? All right, so this is the utility function. The MRS is just the marginal utility of x divided by marginal utility of y, so that's 2. And here the price ratio is 1 over 1/2, also 2, right? So the MRS is the same as the price ratio, so that's this picture, right? The indifference curves, one of them is coincident with the budget constraint. The indifference curves are otherwise parallel to the budget constraint. So let's see, Eden must consume more of good x than good y. Nope. Must consume less of good x than good y. Nope. Must consume equal amounts of both goods to in order to maximize utility. This is like the tricky one. It's actually no, because this says Eden must consume equal amounts. No, Eden doesn't have to. Could consume equal amounts of both goods. Doesn't have to. It's not must. Could be anything along here. So it could be equal amounts of the two goods, or it could be anything in between, right? Or it could be all x, or it could be all y. All right, Elodie's utility can be represented by xy, so just standard Cobb-Douglas. Elodie is consuming 5 units of good x, 25 units of good y. What can we say? Well, Elodie's MRS, the functional form is y over x. Evaluated specifically at this bundle, instantaneously, it's going to be 5. So at the particular bundle, the line tangent to the curve there is 5. Now, if you get, that's why it says like small exchanges, because if you get even a little bit down the curve, right, it's got a different slope, right? So after Elodie makes a trade of 5 units of y for 1 unit of x, no longer is Elodie's indifference curve having the slope of 5. It's going to have something less than 5, right? We have diminishing marginal utility. So Elodie is willing to make small changes of x for y that involve giving up 5 units of x for every unit of y received. No, so Elodie would be willing to give up 5 units of y for an additional unit of x. Elodie is willing to give up all of X for Y if received more than 5 units of Y for every X? No, we have this diminishing marginal returns. And so there might be one trade where Elodie is willing to do that, but at a certain point it's gonna well, at different points it'll change. Elodie likes both X and Y the same, so Elodie is always willing to exchange them at the rate of 1. No, that's obviously not what's happening. Elodie would be always willing to trade at any price if Elodie lacks equal amounts of the two goods. No, because willingness to so if we're thinking about what the MRS is, that's a different question from if you once we start introducing prices. Elodie is going to be interested in trading so as to optimize, so as to keep the MRS equal to the price ratio. And so the rate of trade-off that Elodie is going to be willing to make is going to depend on the relative balance, right? Averages preferred to extremes. And the marginal rate of substitution changes along the curve to reflect that. I've got a video on reflecting like a past quiz question. It has to do with like Cobb-Douglas. I'll try to remember to link that. All right, so now I want to think about the short answer portions. So suppose Emily has $24 with which to purchase donuts and lattes, 12-ounce lattes. Lattes cost $4 for each cup. Donuts have a special pricing scheme for $6 or $2, thereafter $1. That'd be awesome. We can represent Emily's preferences over donuts and lattes with the following utility function. DL is going to be D plus beta L. What does Emily's budget look like? Draw a picture with lattes on the vertical, donuts on the horizontal. How many lattes can Emily maximally afford? How many donuts? And then how does beta in Emily's utility function affect the optimal consumption bundle? Show and explain your complete reasoning. All right. So Emily can maximally afford M over P, which is 24 over 4 or 6 lattes, or can maximally afford 18 donuts. We have to actually do some calculation to get those 18 donuts. So here's what the budget constraint looks like. So this is income divided by the price of lattes. So step 1 is always let's find the vertical intercept of the budget constraint, or let's find the intercept that's not where the price is not changing. That's this. Step 2 is let's find my expenditure to the kink. So the kink happens at 6 donuts. Getting to 6 donuts is going to cost me $12 because the price for the first 6 is $2 each. Emily has $24. Emily lost $12 to get to this point. Emily now has $12 with which to buy additional donuts at a price of $1 each for a total of 18 donuts. Or Emily can go from this point here, buy no more donuts, but buy 3 lattes because the lattes are going to cost $4, and with the $12 remaining, Emily can afford 3 lattes. So that's why this point is 6.3. The slope here is going to be 1/2. Slope here is 1/4. Yeah, I know. It's minus 1/2 and minus 1/4, but okay. So this is going to be the steeper portion, kind of. This is going to be the flatter portion. That's the picture. That's enough for part A. Got it. What about for Emily's bundle depends on beta? Okay, so let me go over this portion first. Emily's MRS, it's 1 over beta. We've got that here. That's just like 1 is the marginal utility of donuts, beta is marginal utility of lattes. Got it. We're going to compare this to the price ratio. And then for different values of beta, Emily's going to have a different optimal bundle, which has to be captured in our demands for Emily's optimal bundle, right? We're asked like, how does beta in Emily's utility function affect the optimal consumption bundle? Well, we have to like fully specify how it affects the consumption bundle. For full credit, there's like a lot of things we have to talk about that can happen. So the first thing is like just the really obvious ones. We can get a solution that's Allie. We can get a solution that's Alex, right? So how does this happen? Well, let's see. So if beta is bigger than 4, Emily's MRS is going to be less than 1/4. It'll be flatter than the whole thing. That's like this one. I wrote this number 1. It's like a really flat indifference curve. So the really flat indifference curve is the highest possible super flat indifference curve is going to cross at our Allie solution. All right, what if beta is smaller than 2? Now the MRS is going to be bigger than 1/2, right? Think of like suppose beta is 1, that's smaller than 2, then the MRS is 1, that's bigger than 1/2, so that's going in the right direction. So I drew like a super steep indifference curve that would cross down here. That'd be our Alex solution, our all donut solution. Okay, there's some other things that can happen. So we have our Alex solution, we have our Ali solution. These are things depending on beta. Interestingly, the budget constraint is convex-ish. The kink can never be optimal. So I don't know if this is helpful or not, but just like envision the indifference curve that would cross at the kink, right? Envision the indifference curve that crosses at the kink. Well, there's always one to the right of it that's going to be higher, that's also going to cross the budget constraint, right? So any indifference curve that's going to cross the kink, we're going to find a higher one to the right, right? So the kink's never optimal, so that's not going to happen. And so that can never be optimal, all right? And so I did this actually, so here, I like the indifference curve argument. You could do this by actually calculating the utilities, and you can demonstrate that as well. Let's see. The other thing that can happen, there's some other weird things that can happen. One is, suppose the indifference curve has the exact same slope as one of these ends. Suppose you have a slope of 1/4. Well, just visualize an indifference curve that's got the same slope as this bottom portion. Higher indifference curves are to the northeast. Oh, sure enough, we can get a higher one that goes up through here. I think I've labeled it with a 5. Suppose we had an indifference curve that's got the same slope as this portion of the budget constraint. Higher indifference curves are to the northeast. The highest one is going to come here. I think I've labeled it with a 4, right? If you have an indifference curve that has the same slope as this, it's not going to be, the solution's not going to be along here. The solution's going to be out here, right? It's going to be the all donut solution. Or if you have an indifference curve that's as flat as this portion, the solution's going to be up here. And then the weird thing that can happen is thinking about what Emily's going to do if the MRS is between 1/4 and 1/2. So let's see, so one thing that's interesting to reflect on is the two intercepts, the donut intercept and the latte's intercept lie on a line with the slope 3. So if beta is exactly 3, such that the MRS is between, is 1/3, or it's between 1/4 and 1/2, then the intercepts lie in the same curve, and then that's a situation where Emily would be indifferent between the intercepts. Otherwise, it's always going to tip one direction or the other, depending on if we have like a relatively flat indifference curve, the solution is going to be lattes. If we have a relatively steep indifference curve, the solution is going to be donuts. And now I'm bounding the notion of relatively flat and relatively steep within the range of 1/4 to 1/2. So, all right. Anyway, I think that's kind of a cool exercise, because it kind of forces you to reflect on some of the intuition about the structure of the problem. All right. So Elijah is going to insist on consuming exactly 3 graham crackers with each glass of milk. Elijah has $12 of income, his allowance from his family. He faces prices. Price of good X is 1, price of good Y is 3. Find Eli's optimal bundle of graham crackers and milk. And then suppose Eli faces the following choice. Either Eli's income can rise to $18, or can just receive the original $12 but get 2 free glasses of milk. Which of these does Eli prefer? All right, so for the first one, we just need to recover Eli's utility function. Just as we did before, the multiple choice question is going to be the minimum of X and 3Y, right? So this is going to be 3 graham crackers with 1 milk, right? Because we'll check one bundle we know Eli's going to like, 3 graham crackers with 1 milk. And sure enough, that fits. All right, so now we know the line through the corners is going to be X is equal to 3Y, or Y is equal to 1/3 X. I'm just going to make that substitution into the budget constraint, and I solve for an optimal level of 6 graham crackers and 2 glasses of milk for Elijah. All right, that's this right here. Now, what is Elijah like between those two arrangements of what can happen with income and prices, or the free milk? Eli's actually indifferent between 1 and 2, right? With income of 18, what's Elijah going to do? If income is 18, the problem changes to X plus 3Y is equal to 18, or 3Y plus 3Y is equal to 18, or 3 glasses of milk, 9 graham crackers. Well, what if we're spotting Elijah 2 free glasses of milk? Now this is the utility that Elijah is maximizing, right? So we're going to have this weird structure where actually, having gotten those 2 glasses of milk for free, to be able to make use of those, Elijah's got to allocate some of the money to graham crackers. Matter of fact, this is going to be 2 times 3 is 6. We need at least 6 graham crackers to be able to make use of those 2 glasses of milk. So we know before anything else, Elijah's going to buy 6 graham crackers, right? 6 graham crackers to be made to be able to make use of those 2 glasses of milk, because 2 times 3. All right. So from this point now, given that Elijah had $12 and has spent $6 on those graham crackers, Elijah has $6 left over, facing the original prices. So x plus 3y is equal to 6. 3y plus 3y is 6, or 6y is 6, or y is equal to 1. So Elijah's going to buy 1 glass of milk, is going to buy 3 more graham crackers. Elijah's going to have 2 glasses of milk and the 6 graham crackers that Elijah had previously purchased to make use of those 2 free glasses of milk. And at the end of the day, overall, Elijah's consumption is going to be 9 graham crackers, 6 plus 3, and 3 glasses of milk, 2 plus 1. That's the same. Elijah's going to be indifferent between those 2 schemes. All right. So the last 2. Elodie has preferences represented by this utility function, nice Cobb-Douglas. These are the prices. Find Elodie's optimal bundle using Lagrangian. And then true or false. If price of good X falls from 6 to 2, Elodie will spend more on good Y. False. We know that immediately, right? We know our Cobb-Douglas demands. If the price of good X falls, what's going to happen? Elodie's going to change the bundle for X, but not change the bundle for Y. And then to show that, we have to show with the Cobb-Douglas demands. Anyway, so for the Lagrangian, I'm going to set up the Lagrangian. It's going to be maximizing by choosing X and Y. It's going to be X to the 3/4, Y to the 4th, minus lambda times this stuff, budget constraint. I'll take the derivative. That's going to be 3/4 X to the minus 1/4. Y to the 4th comes along for the ride, minus lambda 6. And then it's going to be 1/4 X to the 3/4, Y to the minus 3/4 comes along. 1/4 X to the 3/4 comes along for the ride. Y to the minus 3/4 because we're reducing the exponent by 1, and then minus 2y. Or suppose you just hate that, you could take the monotone transformation that I recommend in the solution originally, and you could take the natural log, and it'd be 3/4 ln x plus 1/4 ln y. This ultimately gives way to the MRS of 3y over x, comparing to a price ratio of 6 over 2, which gives us a tendency of y is equal to x. That's this right here. 3y over x versus 6 over 2. I meant to erase this better. 6x over 2 is 3 is equal to px over py. What did I do? I think I lost. Oh, yeah. This is an equal sign here. All right. This stuff equal to this stuff at the tangency gives me this. And then x is equal to y. Let's plug this into the budget constraint. Oh, easy. We've got our demand for x, our demand for y. Good. And then for part B, we can look and see a couple things you could do is you could redo the problem and see what happens. Quicker way is to get our Cobb-Douglas demands, to get our generic demands, which you should show, right? Here I didn't get the generic demands. You should maybe do the general problem and get the generic Cobb-Douglas demands. And once you've got this, we'll reflect on this. So we'll say, wait a second. Elodie's demand for y doesn't depend at all on the price of good x. And so when the price of good x changes, the expenditure on y actually remains the same constant share of Elodie's income. Beta over alpha plus beta times income is the expenditure on good y. Expenditure on good y is just py y star. All right. So what ends up happening if the price of good x, what did I say here? The price of good x falls from 6 to 2. Price of good x falls from 6 to 2. I think we said then Elodie's consumption goes to 6 for x, and then which is 3/4 the income of 16, and then Elodie's consumption for good y stays at 2, which remains a quarter of Elodie's income on good 6 quarter of Elodie's income of 16. All right. Lastly, Owen has preferences represented by the following utility function, 2 ln x plus y. Suppose Owen faces the following prices. Price of good x is 6, price of good y is 3, with income 9. Find Owen's optimal bundle. Then Owen's income falls to 6, while price of good x falls to 2, and price of good y falls to 1. Find the optimal bundle. And then suppose Owen's income falls to 4, prices become 2 and then 3. Assuming no further price changes, what level of income, if any, will Owen buy good y? All right, so for the first one, we're going to compare Owen's MRS, which is going to be 2 over x versus the price ratio 6 over 3. Where the 2x come from? 2 over x come from? Well, the partial with respect to x is 1 over x times 2 is 2 over x. Partial here with respect to y is 1. So 2 over x over 1 is our MRS, which is just 2 over x. That equals 6 over 3, which is 2. So we find that, who's this character? Owen's demand for good X is going to be 1. And then to exhaust the budget, well, 6x plus 3y is equal to 9, or 6 plus 3y is 9. 3y is equal to 3, y is equal to 1. All right, so that's part A. Part B, let's compare 2 over x. That part doesn't change. The MRS stays the same. Price ratio changed to 2 over 1. Owen still wants 1 unit of good X. 2 times 1 is 2. 6 less 2 is 4. And then Owen's going to demand 4 units of good Y. And then lastly, what ends up happening, so lastly, this is the interesting one. Owen's income falls to 4. Prices are 2 and then 3. Assuming no further changes happen, at what level of income, if any, will Owen buy good Y? All right, well, the MRS is still 2 over X. The price ratio is now 2/3. This tells us Owen wants 3 units of good X. If Owen wants 3 units of good X and the price of good X is 2, Owen needs $6 to be able to buy good X. All right. So what about the demand for good Y? Well, you could try plugging this in budget constraint. Owen's demand for good Y is negative. That's not good. We don't even need this part. We just need to say, wait a second. Owen has quasi-linear utility. Owen wants 3 units of good X. Owen's not going to buy Y until Owen's got those 3 units of good X. And you can actually verify that by writing out MUX over PX versus MUY over PY and evaluating at different bundles. And you'll see MUX over PX will be bigger than MUY over PY until Owen gets 3 units of good X. Thereafter, MUY over PY will be bigger than MUX over PX. And we can borrow some of our perfect subs intuition as to what's going on in terms of like the direction they're going to try to increase their consumption. Remember, with perfect subs, if the MRS is bigger than the price ratio, we have our ALEX solution. If the MRS is smaller than the price ratio, we have our ALI solution. If we give those consumers more income, they just keep buying more X or more Y, just perpetually. That's like all they'll ever do, right? If you have a situation, suppose my perfect subs utility, X plus Y is my utility. And suppose the price of good X is 2, the price of good Y is 1. So compare my MRS, which is 1, to the price ratio, which is 2. We've got a steeper price ratio, flatter indifference curves. So that's my ALI solution, right? We know that. Marginal utility of X is 1, marginal utility of Y is 1. Price of good X was 2, price of good Y was 1. X is more expensive. They count the same towards my utility. I'm going to buy Y. What happens if you give that consumer more money? They're just going to keep buying more Y. That's like all they're going to do. It doesn't matter how much. They have $1 million. They're just buying Y. What's driving this is the relative prices, and then compared to the preferences. We can borrow that logic here with Owen, and we have the situation where up until Owen gets 3 units of X, Owen's buying X. And then after Owen's got 3 units of good X, things change, and now Owen just wants Y. And then beyond, so Owen needs 6 units of income to buy the bundle. Beyond 6 units of income, Owen will start buying Y. More properly, Owen requires 6 units of income to afford the bundle, and then at these prices will not purchase Y until Owen's income exceeds 6. Anyway, that brings us to the end here. I hear my puppy upstairs, and so I'll need to check on what is the matter. But anyway, hope you enjoyed this video, and I'll see you next time.